There are two types of atoms. There are diamagnetic atoms and paramagnetic atoms. And here's the difference. Di, meaning two, diamagnetic atoms are atoms in which there are no unpaired electrons. Everything is paired up, right? Di, right? Two. Everything is paired up. Every orbital has a half arrow pointing up and a half arrow pointing down. There are no unpaired electrons in all of the atoms. So, for example, calcium, zinc, argon, those are all diamagnetic elements. So why don't we start? Why don't you give me the noble gas configuration of calcium, zinc, and argon? Write that down somewhere. And then what I want is I want the lines with the half arrows. So I want the noble gas configuration for calcium, zinc, and argon, and I want the lines and the half arrows, and we are going to confirm that these are indeed diamagnetic elements. Go ahead. I'm going to do them on the board while y'all do them at home. All right, folks. Hopefully, this is what you wrote. Hopefully, you wrote calcium is an argon in bracket 4s2. Zinc is an argon in bracket 4s2, 3d10. And argon is a neon in bracket 3s2, 3p6. And hopefully, you can see everybody is paired up. We got the half arrows. We got the lines and half arrows, and everybody's paired up. So you can confirm, indeed, these are all diamagnetic elements. Diamagnetic. What does that mean? That means these guys cannot be influenced by a magnetic field. There's nothing you can do to make calcium, zinc, or argon magnetic. They have no magnetic properties. Magnetic properties come from unpaired electrons. What do we call unpaired? What do we call elements with unpaired electrons? We call them paramagnetic. P-A-R-A, magnetic. So some examples of paramagnetic elements would be sodium and nitrogen and iron. Here's what I want you to do. I want you to write the noble gas configuration for those three elements. I want you to do the lines and the half arrows, and I want you to confirm that they do indeed contain at least one unpaired electron and that they are indeed paramagnetic. Go ahead. All right, sodium is a neon in bracket 3s1. We got one unpaired electron. Nitrogen is a helium in bracket 2s2, 2p3. We got three unpaired electrons. And iron is a argon in bracket 4s2, 3d6. We got four unpaired electrons. All those atoms have at least some amount of magnetic properties. Now, it's not quite as simple as this, but in general, the more unpaired electrons you have, the more magnetic you are. Okay. I'd like to do one more, so hopefully you can see how they are all paramagnetic and could be influenced by a magnetic field. I would like you to write the noble gas configuration of copper. Go ahead, give me the noble gas configuration of copper, please. All right. Hopefully you remembered copper is one of our exceptions. You would think that copper would be an argon 4s2, 3d9. But then you remember D9s don't exist. They steal an electron from the S and put them in the D. They're a 4s1, 3d10. So the question is copper paramagnetic or diamagnetic? The answer is it's paramagnetic. It's got one unpaired electron right there. It's a paramagnetic element, which means copper should have some degree of magnetic properties. But if you hold a magnet to a penny, it ain't gonna stick. Copper's magnetic properties are very, very, very low. In fact, you need a device called a gooey balance to be able to pick this thing up. It's a pretty crazy device. What you do is you get like a spring, okay, and you put your sample, okay, like you put your piece of copper on that spring, and on each side of the spring is an electromagnet. You turn the electromagnet on, and you see if that spring gets stretched. And if you have this attached to a gooey balance, it can actually detect, if you have a strong enough magnet, that the copper is attracted or repelled by the magnetic field, and you actually will get a stretch. Again, that's called a gooey balance, G-O-U-Y, gooey balance. I've seen one once. Okay, not used very often, but you know, if you say, wait a minute, man, copper is not magnetic, you're right. It's not very magnetic. It's slight paramagnetism actually can only be detected using a really sensitive instrument called a gooey balance, but it is there. It is there. It's true. There you go, man. Learn something every day. All right. Paramagnetism versus diamagnetism. Make sure you know those two terms. Let's see what else is on the docket. I think isoelectronic species is next, so let's talk about that. We briefly talked about this on I don't even know what day it is. I think it was today, Wednesday. So we briefly talked about this on Monday. Isoelectronic means you have the same electronic configuration. Means you have the same electronic configuration as something else. Cool. So what are some examples? Well, I want to list an isoelectronic series. Isoelectronic series. This would be a series of elements that are isoelectronic with one another. So what I like to do, if I'm going to come up with an isoelectronic series, I pick a noble gas. So let's start with a noble gas like argon. And now I'm going to create some ions that would have the same electronic configuration as argon. So we can go past argon. So argon's element 18. Let's look at potassium. Well, potassium has 19 electrons, but if we give it a +1 charge, now it's isoelectronic with argon, right? Because potassium would be an argon 4s1. Take its electron, there goes the 4s1, is isoelectronic with argon. And then calcium +2. Calcium is an argon 4s2. Take 2 of its electrons. Calcium +2 is isoelectronic with argon. What else we got? We can go the other direction if you're looking at a periodic table. Chlorine is right before argon. Give it an extra electron, make it chloride. Now you're isoelectronic with argon. We can go one back. Sulfur, 16 electrons. We need 2 more to look like argon. The sulfide, S-2 or 2- ion, that would be isoelectronic with argon. This is an isoelectronic series. In a moment, we're going to get into atomic size, and we're going to actually talk about the fact that they are different sizes, okay, but they have the same electronic configuration, these 4 ions and that neutral element there. What's the other thing we're going to talk about? Keep in mind they are different. These are still different elements. They have different numbers of protons, right? When you add a charge, you are just changing the number of electrons. So this is still sulfur. It's just got the same electronic configuration as argon. This is still calcium. It's just got the same electronic configuration as argon. They are isoelectronic with one another. So awesome word right there, isoelectronic. We did valence and core electrons last time because we were superstars on Monday. My goodness, we were crushing it, yo. All right, take a second here. Which of these elements 4+ cations would have the following electronic configuration? Which of those elements would be in their 4+ state? Would be a krypton 4010. You got this, folks. Woo! Back to it. There we go. Which of those 4+ ions would be a krypton 4010? And the answer is tin. The tin +4 ion is a krypton 4010. Why? Let's talk about it, man. So here's krypton, and then here's your 4010. That's yttrium to cadmium. So we got to take away 4 electrons. Well, that would be the 5s2 and the 5p2. So neutral tin is a krypton in bracket, 5s2, 4010, 5p2. Take away the 5p2, take away the 5s2, the 2 electrons here, the 2 electrons there. You're left with a krypton 4010. That's the tin +4 ions. So I'm hoping y'all got that. Kind of a different way to ask one of those questions in multiple choice form. Which of these, ladies and gentlemen, is the correct electronic configuration for the iron +2 ion? Go ahead. Which of those is the correct electronic configuration of the iron +2 ion? All right, well, let's do just that. Iron, living here, it's an argon in bracket, and then a 4s2. My God, I cannot write with this mouse, man. 4s2, 3d6. So if it's going to be the iron plus 2, we need to take 2 electrons away. You take away the highest energy electrons. That makes this an argon 3d6. So this guy's neutral iron right here. Take those 2 away. You got yourself an argon 3d6, man. Rock and roll. Which of these guys is diamagnetic? Woo! I would write out the Nobel gas configuration of these and try and see who's got all their electrons paired up. You got this, folks. I would start by writing the full electronic configuration of tin. And taking a look here. So regular old tin, or not full, you could do noble gas. Regular old tin is going to be a krypton in bracket. And then it gonna be, where's that? 1, 2, 3, 4, 5. It's gonna be a 5s2, 4d10, 5p2. Bam, 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 bam. So regular old tin, that is not diamagnetic. Regular old tin is paramagnetic. So not tin. Not 10. What about 10 plus 2? Well, let's take the 2 highest energy electrons away. That'd be those 5p2s. If we take the 2 highest energy electrons away, yeah, 10 plus 2 is indeed diamagnetic. Check. What about 10 plus 4? What if we take 2 more electrons away? Well, the next highest energy electrons would be the 5s's. And yeah, you know what? 10 plus 4 is as well. Both tin plus 2 and tin plus 4 are diamagnetic species. Neutral tin, though, paramagnetic. Hopefully that one went well.